Hi everyone, I'm here to do making a video of the Newton's second law of rotation practice sheet. Away we go. A thin hollow sphere rolls down an inclined plane that is 20 degrees above the horizontal. What is the acceleration of the rolling sphere? So to get things started, just maybe a little diagram of this sphere. And the free body diagram looks like this. We have an mg vector, which is the weight. We also have a normal force vector, and then there's a friction vector that is applied right at the base of the circle. To do the acceleration, the sum of the forces equals m times a being the goal. There's two forces that are crucial here. I'm going to give them a color. There's friction, and then there's Fp. Now Fp is the component of mg that is parallel to the incline, and that's why I put it in red. It's really technically not part of the free body diagram, but it is crucial and important, especially for the math part of this. So this is going to be Fp minus F in opposite directions equals m times a. Fp is mg sine theta minus friction equals ma. Now the frictional force is a little bit challenging here because it's a static friction. And what we have to do to figure that out is we have to look to rotation, or the rotation of the object, to figure out that static friction. So because the object rotates, the only way it can rotate is if a torque is applied. So torque equals I alpha. This is going to take care of the rotational part of this problem. And the torque really is just the radius of the circle multiplied by the force of friction, and that equals I alpha. And this force being the force of friction. If we solve for force of friction, we get I alpha divided by the radius. I is the moment of inertia of the disk, which is 2/3 mr squared times alpha, and then we're dividing by r, so one of the r's actually goes away, and we're left with 2/3 mr alpha. Now, the goal here is to eventually take this value for friction and substitute over here, so we know we don't have to calculate the force of friction, we can just calculate the acceleration. But before we do that, we need to convert this angular acceleration into a linear acceleration. So for that, I do a equals r alpha. Alpha equals a divided by r. Do a substitution. I get 2/3 mr a over r. So it turns out that the force of friction is really equal to 2/3 ma. I can now go back to the left side of the screen and write mg sine theta minus 2/3 ma equals ma. Turns out since every term has a mass cancels. G sine theta equals a plus 2/3 ma, and that comes to, let's see, G sine theta equals 5/3 a, so a equals 3/5 G sine theta. I'm plugging in the numbers. 3/5 times 9.8 times the sine of 20. A equals, I think I had 2.01 seconds squared. Sorry, 0.01. We got it right out of there. That's the basics here of that. Let's see, what's the next question? What would the acceleration be if the rolling object were the same mass and radius, but a ring instead of a sphere? Well, a ring has a moment of inertia that's different. It's just mr squared. And so what we would do is, if we kind of steal a little bit of our work from above, maybe I'll take like from here, let's say mg sine theta minus friction equals ma. And maybe from here, I could say that friction equals I alpha divided by r. The friction is just mr squared divided by r times alpha. So the square goes away. And then the alpha value, like we did above, is just A divided by R. So the R goes away. So the frictional value is just MA in this case. So with a substitution here, I get mg sine theta minus MA equals MA. Masses cancel like above. G sine theta equals 2A. So A equals G sine theta divided by 2, which is whatever that value is. Let's see, 9.8 sine 20 divided by 2. So A equals 1.68 meters per second squared. So it's a little bit slower of an acceleration. The ring, again, because the mass is towards the outside, even more so than a sphere, gets a slower acceleration. So on to the back. The Atwood machine. Lovely device. Let's see. Two masses are suspended from a pulley, Atwood machine. The pulley is a solid disc, so it's 1/2 mr squared. It has a mass of 0.2. I'll label that. Let's see, I'll make pulley capital M, 0.2 kg. Has a radius of 0.15. A constant torque of 0.35 meter newtons due to friction. That's a little new. The suspended masses, mass 1 is 0.4, mass 2 is 0.8. So just to get a quick idea of what's going to happen here, there's going to be an acceleration that way, a turning that way, an angular acceleration. So the friction is going to oppose that. So torque due to friction is 0.35 meter newtons. That's going to be a clockwise friction. And the first thing I'm going to do is I'm going to get started by looking at each block individually. So start off, we'll do block 1. Block 1, the forces are mg and tension 1. Tension 1 being a little bit bigger than m1g, because it's going to move up as it's the smaller mass. So sum of the forces equals m times a. Tension 1 minus m1g equals m1a. I'm going to solve for tension, knowing kind of what's coming. This is m1a plus m1g. I'm going to repeat for block number 2. So what I'm going to try to do initially is I'm going to try to write an equation for each piece of this system. 3 pieces. Block 1, block 2, and then the pulley. And then I'm going to try to put them all together to find the acceleration. Block 2 has 2 forces acting on it. We have m2g, which would be larger than m1, and then tension 2, which would be smaller than m2g. I can still apply Newton's second law translational form. It's going to be sum of the forces equals ma. Sum of the forces is m2g, that's gravity's pull, minus tension 2 equals m2a. Solving for tension 2, I'm going to get m2g minus m2a. Now I have an expression for tension 1 and tension 2, which is useful because I'm going to need those in a minute after I write an equation of motion for the pulley. So the pulley has 3 torques acting on it. There's tension 2, which is causing torque 2. There's tension 1, which is causing torque 1. And then there's the torque of the friction. So the sum of all these torques equals I alpha. This is Newton's second law, rotational version. The three torques involved are torque 2. That's the biggest one because it's going to twist in the direction of object 2, which is torque 2, minus torque 1, minus torque friction. And that equals I alpha. Each torque is the result of a lever arm value or radius multiplied by a force. So this is R times T2 minus R times T1 minus torque friction. I don't need to calculate or do R times F for the frictional torque because they tell me exactly the value. I can kind of see that by looking at these units right there. It's meter newtons. It's already given to us, so we're going to leave it as is. And that equals I alpha. I'm going to do a little work in this next line to write down where I is. It's 1/2 mr squared, and I'm also going to substitute, instead of alpha, I'm going to convert that to a translational acceleration. Alpha equals A over R. So I'm going to write A over R, one of those R's. The R in the denominator is going to cancel. Let's see here. Next step, I want to start to substitute tensions. Get rid of these tension values and write them in terms of M's and A's. So let's see, I'll go over here a little bit. R times tension 2 is M2G minus M2A minus R. Tension 1 is M1A plus M1G minus torque friction equals 1/2 mRA. Next step is I'm going to distribute the R to every term. So R M2G minus R M2A minus R M1A minus R M1G minus torque friction equals 1/2 mR, capital M. Everything in this equation is known except for acceleration at this point. I just need to move things around to get the accelerations all on one side of the equation. So that's my next step. So R M2G, let's see, minus R M1G minus torque friction equals 1/2 mRA plus R M2A plus R M1A. Factor out R2G minus, let's move my screen up a little bit here, R M1G minus torque friction equals A times this quantity, 1/2 mR plus R M2 plus R M1. And then just kind of final equation, final stuff here, algebra. R M2G minus R M1G minus torque friction divided by 1/2 mR plus R M2 plus R M1. In class we did an example where there was no frictional torque and the R values all canceled. And that would make things a lot easier, but since the frictional torque value doesn't have an R in it, I left everything in. I'm sure there's a way that you could do it by finding the force that's acting because of friction, but we're not going to bother. I'll just plug in the numbers here. I have everything I need. The radius is, see if I remember, I think it's 0.15, 0.8, 9.8 minus 0.15, 0.4, that's 9.8, minus 0.35, that was that torque, frictional torque value, divided by, here come the masses again, 1/2, let's see what the pulley was, I forgot, 0.2, 0.2, there's a radius, so the pulley was 0.15 minus, or excuse me, plus in the denominator, times 0.8 plus 0.15 times 0.4. So you can kind of plug all that in. And you finally end up getting 1.22 meters per second squared for a very difficult problem. But I hope that some of this helps you a little, and if you need to rewind or rewatch or ask questions, so please do so. And I hope it helps some doing the homework with me. Thanks.